All right, so we're going to be looking at some linear algebra topics. We're going to split it into vectors, first half, matrices, second half. So we're going to vector operations. What I mean by operations is scalar multiplication, addition, and subtraction. So we're going to look at that today. But a vector is a quantity with magnitude and direction. Some ways to represent vectors are with a little arrow over the top of it. From P to Q, that's the vector from P to Q, point P to point Q. Sometimes we'll use a single letter V, U or V tend to be common, but oftentimes we talk about velocity vectors. Or a V with a arrow above it. All those are representations of vectors. A vector is, once again, quantity with a magnitude and direction. Now, the magnitude can be found just using the Pythagorean theorem. Trig comes back into play here. And direction could also be found by using inverse tangent. Okay, so trig is back in the mix. Magnitude is the length of a vector. Okay, the length of the vector. It's the hypotenuse of the right triangle formed when you draw the vector. A little slightly different symbolism here. We use double absolute value symbols, if you will. It's called the norm or magnitude of a vector. Sometimes it's called norm, N-O-R-M. But magnitude of a vector, double absolute values, it's just the square root of a squared plus b squared, which is exactly Pythagorean theorem. So that's how we find the magnitude. And when it comes to direction, you can find the direction or the degree measure up from the horizontal or up from, sometimes it's down from north, and we're talking about airplanes. Things it's based off of north. I'd say a certain degree measure east of north or west of north. Component form is what the vector would look like if the initial point was at the origin. So that's what we're going to do. So we're going to take a vector formed from point P to point Q, and then we're going to translate it to the origin. And then we would be measuring our degree measure up from the positive x-axis, and the length of the vector is just the hypotenuse of our right triangle. In order to translate the vector, all you have to do is subtract the x coordinates of the point, and that will give you the value a, which is the horizontal component of the vector, and then subtract the y coordinates, and that will give you the value b, which is the vertical component of the vector. And the symbol we use is, it looks like the greater than less than symbols here. They look like, but a little different symbolism used here for component form. All right, scalar multiple of a vector is if v is multiplied by a scalar k is just a constant. So if v is multiplied by a scalar k, the result is a vector k times v. That symbol means such that the magnitude of kv is equal to the absolute value of k times the magnitude of v. So all that the scalar does is if you have a vector that is 2 units long and you multiply it by a scalar that's 3, then you now have a vector that's 6 units long. It just triples the length of that vector. That's all that it does. So the scalar multiple Scalar changes the length of the vector or multiplies it by a certain value. Or if it's a fraction, it would divide it, make it smaller. If it's a negative number, it'll take the vector and send it in the opposite direction, just like with our polar coordinates. Remember that? So just send it, if r was negative, it sends it in the opposite direction. So kv is either in the same direction as v or the opposite if k is negative. So it's helpful to have maybe 3 different colors. So if you don't happen to have any colored pencils or highlighters with you, have head color. So if you'd like a couple more colors to add, we'll put that up here. It's trash. It is trash.
Oh, you're talking about our essays?
Yeah.
Yeah. I didn't know what to do with it.
I don't know either.
It's an awful.
So with your 3 different colors in here we go. We're going to start by plotting PQ and just putting an arrow on the end of it, making it into a vector. So P is at the point 2, negative 3, so 2 over, negative 3 down. 2, negative 3, that's P. And then Q is at negative 1, negative 4, so negative 1, negative 4. So it's going from P to Q, and I'm going to do that in blue. P to Q, and okay, I guess that's okay. So P to Q. So the arrow's heading towards that 3rd quadrant there. So we're basically going to translate this up to the origin. Okay, we're not going to change the direction or magnitude of it. We're just going to move it up to the origin. Translate it up there, make it a little easier for us. So in a different color, I'm going to translate it. Now, what I had said up here, you can see it at the very top of the page up here. The vector AB is such that A is equal to x2 minus x1. So it looks like this. Here's my vector V. It's going to be such that A is equal to, so just make your left symbol looks like a less than symbol. And I'm going to subtract the x-coordinates. So negative 1 minus 2. And then the other coordinate is negative 4 minus negative 3. And so my vector V is equal to negative 3, comma, negative 4 plus 3 is negative 1. So negative 3, negative 1. You could probably do this by eye, but this tells you exactly the end point of the vector starting at the origin. Okay, so by just subtracting the x-coordinates and subtracting the y, you are translating it to the origin. Okay, so negative 3, negative 1 is right here. And we're going to label that vector v in a different color. The 2v, we're going to write right underneath it. 2v is literally taking the component negative 3 and negative 1 and multiplying them by 2. So 2 times negative 3 and 2 times negative 1 gives me a new vector of negative 6, comma, negative 2. That you could probably also do just by looking at it and, doubling each of the dimensions. So negative 6, negative 2 is out here. So in red, I have my vector 2v. So 3 different colors there. Take the original vector, translate it to the origin, then go ahead and double the vector. You've got it. Yeah.
Why do you need 2v and v?
That's just what I asked for. I asked you to find V and then find, or, well, ultimately to find 2V, and I'm taking it in steps, I guess. So I'm started with the vector from P to Q, translating it to the origin, and then doubling it. That's all. So, then I asked you, I think, for the magnitude of the vector 2V, right? So, let's see, graph V in one color, then graph give it multiple of V in another color. Okay, that's it. Find the magnitude form of PQ called V. Okay, so I wanted you to find the magnitude just of PQ called V. So what would the magnitude here be of our green one here? So the magnitude of V, and you could find the magnitude of 2V as well, but the magnitude of the vector V is the same as the magnitude of PQ. It's the same length. It's just been translated. So it's square root of -3 squared plus -1 squared, which is square root of 10. So there's the magnitude. We don't need the magnitude to be able to draw it. We just need coordinates. But that's the magnitude of the vector V. It's the square root of the A component squared plus the B component squared. All right, I want to demonstrate number 2 just to show you what it looks like when you have a negative scalar. Okay, it just sends it in the opposite direction. So we're starting once again at P, -4, 5. So -4, 5. Right here, there's P. And then -2, 8 is Q. So we have this vector going from P to Q. And we're going to translate that thing down to the origin. So we could probably do the subtraction in our heads here now that we know what we're doing, right? So -2 minus a -4 would be -2 minus a -4, 2. And then 8 minus 5. Let's just see if it looks right here. That looked like a translated vector that's the same direction and the same magnitude. Okay. So there's a built-in visual check here. Magnitude of V. We could probably do that in our heads as well. Is equal to the square root of what? 2 squared? 3 squared? Good. There we go. We got it. And then if I want to find -3V, how is that going to compare to V here? It will be negative, so it's going to send it in the opposite direction. And so it's going to look like this. -6, comma, -9. If you just know the components A and B and just plot the point, and then connect the origin to that point, you've got it. Okay. So -6, -9, it's right here. There is -3V, and we'll label it as such. That's it. Really easy to do. You can see how it connects to our polar coordinates and things like that too. Any questions on the first two? I would like you to try 3 and 4 on your own, and I'll wander around and see how you're doing on it. So try 3 and 4. See if you can go ahead and find the new vector. If you we're good on. Are we good on magnitude? Let's just find the new vector, please. Okay. However you want to do that. You may even be able to skip, that original step. I don't know if you can translate it right away. If you'd like to, you can. Just use 2 colors. So place it on the origin right away, and then find 4V, and then same thing over here. Find -V. I'll come around and check on and see how you're doing, and some feedback from you. So let's talk about vector addition and subtraction. And this relates to matrices. A vector is kind of like just a small matrix, and we're going to look at those in the second half. So there's a connection there. But vector addition, you just do it what's called component-wise. In other words, if you're adding two vectors, you just add the A components and you add the B components, you have a new vector. It's really simple. So that's what that's saying. You have a vector U and a vector V. Vector U plus V is A plus C and B plus D. And then subtraction, you could guess on what that is. U minus V is just A minus C, B minus D. It's the same as adding the opposite of V, if you want to think of it that way. So we use three different colors here again. So we use the three color scheme to show you what's happening when we add U plus V. You should have a geometric understanding of what it means to add vector V to vector U. All right, so I'm going to graph vector U here in blue. So we have 4, 5. So 4 over 5 up. So use one color. 4 over 5 up, and then draw your arrow. That's vector U. I'm going to use a different color for vector V. So negative 2, comma 4 is vector V. It's vector V. So just wait and watch what I'm going to do. I'm going to show you a translation that I can do on the smartboard. You're going to have to use kind of the color scheme to do it. But here's what we're literally doing when we add vector V to vector U, is we tack on vector V to the end of vector U. It looks like this. And then we get our new vector from the origin to the end point of that. Right? I mean, that's literally what we're doing. So I'm going to go back here. Oops. I just separated all those out. That's a bummer. Okay. So separated into the pieces. Let me redraw it here. So what we'll do is go ahead and we're going to create the same vector. It's the kind of parallel principle here, but another vector parallel to this green vector V, and we're going to build it off of the end of vector U. So we'll go ahead and do that together. So here I've gone 2 left and 4 up. So from the end of vector U, I'm going to go 1, 2 left, and 1, 2, 3, 4 up, and just create a parallel vector here. Call it vector V. I did them in the same color, yeah. Just showing you that it's the same length, same magnitude, same direction. And then my resultant vector will be U plus V, okay? So this is a geometric representation of adding vectors. Now you can literally do U plus V is equal to, according to the definition, 4 plus negative 2, comma 5 plus 4. I mean, I don't have to do this geometric representation to get my resultant vector U plus V. I just add the components. So it's 2, comma 9. And so that's about where I should be here. I think I am 2, comma 9. Yep, it's fairly accurate. So this is the resultant vector U plus V. That's it. I think I had asked you to find the magnitude of U plus V. We can do that. It's not a problem. We'll do it just one time here. The magnitude of U plus V is equal to the square root of 2 squared plus 9 squared, using the components of that red vector U plus V. 4 plus 81 is 85, so square root of 85. That's the length of the vector from here to here. Just think of the red vector there, U plus V, as the hypotenuse of the right triangle formed. 2 to the right and 9 up. And then we're right back with trig. And you can see that even if you took something like this, you see the blue, green, and red vectors, say this was just out in space and it's not on a coordinate grid, I can still use trigonometry to find any lengths and any angles I want to find. So that's where it connects to trigonometry. This triangle made of the 3 different colors is not a right triangle. So law of sines, law of cosines would apply. The triangle formed just between the legs going 2 right and 9 up of just the red piece here. That's a right triangle, so you could use right triangle trig to find the length of that. Okay, number 6. Let's do a geometric representation here. We have -5, comma 2. That's vector u. And then we have 7, comma -9. So 7 over -9 down. So 7 right, 9 down. That's going to be vector v. And I'm adding u plus v. So I'm going to take vector v and place it where? And place its endpoint, I just accentuated here, on the end of u. Now, if that's confusing, you can always just add the 2 here and get a new coordinate, and you'll know where it ends, and then connect the end of u with whatever coordinate you get when you add the 2 together. It looks like this. -5 plus 7 is 2. 2 plus -9 is -7. So I'm going over 2 and down 7. And now I know where my endpoint is going to be. So if I took this, you can see it here, just translated it over here. Oh, there, that should be my endpoint. So, oh, no, it did it. So I can't do that again. It just separated them all. So right here, I'm going to go from here to here. And that is also vector v. I'm adding it to vector u. And if I connect from the origin down to here, I have my vector u plus v. So there's a geometric representation of the vector u plus v. And then, of course, you could find the magnitude. You could find the direction using inverse tangent if you wanted to. You could call this a negative angle. You could go the positive angle all the way around. It just depends on what the application is. All right, we're going to do u minus v and 2u minus 3v together. And I have some problems for you, just a few problems for you to try. I think maybe 6 of them. It's just adding and subtracting vectors, scalar multiples, doing a geometric representation of them. All right, so we'll do u minus v here next. U is 7, 3, so go over 7, up 3. There's u. And then I've got, in a different color, vector v. It's 9 over 7 up. Now I'm going to do u minus v. It might be helpful here to just go ahead and do the subtraction. So u minus v. Remember, it's u minus v. If I had v minus u, that would be different. This is u minus v, so I'm going to do 7 minus 9, comma, 3 minus 7. So u minus v. 3 minus 7. So that's -2, comma, -4. So -2, -4. So here's my resultant vector down here. That's u minus v. Here's how I end up there. If I were to take v and actually think of it as u plus a negative v, I would first find negative v. So negative v would be the exact opposite of this. So instead of being 9, 7, it would be -9, -7. So here's negative v. There's negative v. And then I'm going to add negative v to the end of u. It's the same thing as subtracting. So right here, And then if I drew, I already know where it ends. So there's negative v right there. I almost need a fourth color for this. But what I've done is I've taken v, found negative v, you with me? From v to negative v. It's just taking the opposites of each of these coordinates. Okay. Same length, 180 degrees opposite direction. Take this thing, tack it on to the end of u, and it's equivalent to doing u minus v. I'm doing u plus negative v, which is exactly the same as u minus v. Now, in the end, my resultant vector in red here is as easy as subtracting the components of u and v. I mean, it's not hard to do. Quick subtraction, you already know what the resultant vector u minus v is. But a geometric representation is take v, negate each of these, and then add negative v to the end of u, and you land at the same spot. So it's a geometric representation using what we call the parallel principle. Have you guys talked about the parallel principle in physics? Did you guys talk about it? Quite a bit? Okay. A bit of geometry there. Okay. Number 8, 2u minus 3v. Okay, just to show you, let's not make the craziness of colors here. Let's just find 2u minus 3v. Here we go. Can we do it? A little bit of arithmetic, maybe? So here it is. It's equal to this. 2 times u would be 8. And then minus 3 times v, so minus 9, right? Comma. And then 2 times u, you're going with the second component, is negative 4 minus 3 times v would be negative 3 times negative 1 is positive 3. Okay. So it's just negative 1 comma negative 1. That's my resultant vector 2u minus 3v. So negative 1, negative 1. This is 2u minus 3v. And we could find its magnitude. What is its magnitude? We're asked to find the magnitude. It's square root of 2, yep. You could even tell me the direction in degrees in lots of different ways, right? What's the direction? How about in degrees? How about positive degrees between 0 and 360? Okay, it's a 45-degree reference angle, good. So you could say 45 degrees down from, due west if you wanted to. What's that? It is. You could say 5 power 4 radians. Yeah, you could. It's 225 degrees positive. It's negative. What is it? Negative 135. So there's lots of different ways you could do it in terms of telling me exactly which direction it's going, and it depends on what we're talking about. I don't know. You guys probably have different rules in physics in terms of what you do, but mathematically speaking, they're all equivalent, right? So. And that's the power of mathematics, is we need to recognize those equivalencies. That's a big part of mathematics.